Good afternoon, everyone. Welcome to the week first of the live sessions for the finite element method. I'm your PMRF TA, Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So, you all people, I hope you all people have enrolled yourselves in the NPTEL online course, that's the finite element method, that is going on almost 1 week has completed. And at the end of 1 week, as a part of my PMR FTA-ship, I have been assigned that I will be your assisting TA for the problem solving session or any doubts you people might have. So I request all of you to first enroll yourselves into the finite element method course that is there on the NPTEL website. After that, once you enroll, you download all the assignments and also the daily works that have been assigned there, and try to solve all those assignments by yourself first at your place. And then, if you people have any doubts, then you can raise those doubts in the weekly sessions that I will be conducting every week on Saturday between 3 to 5 p.m. So this 2 hours slot will be very beneficial for you, in which first hour I will be teaching you something regarding the concept or the regarding the problems, and in the last hour I will be hearing to you to your respective doubts. So I have been doing this NPTEL ship from last 2 years, wherein I have taught the courses like structural analysis first, design of reinforced concrete structures, and structural dynamics. And those NPTEL sessions were quite successful, and I got a very good feedback from the students. I hope you people will be also keen to learn something from me, and I also will be learning something from you people. So this is the first live session of this finite element method course. I hope you all people will enjoy this course. You will enjoy doing the assignments. You will enjoy giving the examinations. And at the end of this course, I hope you will be different what you are at now this stage, or what capability or what techniques you had learned at this stage. You will be a totally different person at the end of this course. Like, you will be equipped or you will be having an hands-on experience on finite element method, which is one of the most powerful numerical methods till date humans have invented. So this is a very fundamental course in civil engineering, not in civil engineering, in all fields of engineering. And since this is the course offered by civil engineering department, especially the structural engineering division specialization, so it will be mostly oriented towards the civil part, like this structures and all. One more request to the students is that if the people are not interested in joining the live sessions, you just don't join the live sessions and then keep your tablets and the iPhone, computers at their respective place and don't listen. I request you just disconnect from the live session. These sessions will be recorded and YouTube will be uploaded on the YouTube. Then YouTube links will be shared to you by the NPTEL team, IIT Madras. You can then access those videos online through YouTube, and then can play those videos at your own pace. So this first live session will be an introduction live session, wherein I will be describing some of the basic concepts regarding the finite element method. I will be giving you the big picture why this finite element method was invented and how this finite element method is superior to other methods that were initially existing at that, and what was the necessity, why was this method even discovered. Why can't we do some things like, no, why can't we get the solutions to our problems manually or by writing some other computer code. Uh, so there is a long story behind it. I hope all of you people will keenly listen to all the concepts, because numericals, everyone can do numericals. Everyone can just memorize the algorithm, memorize the steps to be done in the finite element analysis, and just do the things. But at the end of the day, he will not be having a big picture or the big concept behind the finite element analysis, why we actually require this finite element analysis. So I hope this live session series will be beneficial for you people. So if you have any doubts, you come up with those doubts, ask those doubts in this live session, and then I will see those doubts as at my place and then come up with the solutions to those doubts. And if you have any numerical problem doubts, I will be trying to solve those numerical problems in these live sessions, and will be giving you the solutions to those problems as well. I welcome again you to finite element method course. So introduction to finite element analysis. So what is finite element analysis and why we require it? First, we will see the big picture. Big picture of, I will write small finite element. Either finite element analysis, the process of doing analysis of the things, or we can write finite element method. You people don't confuse between the two terms, okay? FEM, some write FE or FEM, both keep the same meanings in the big picture, like the analysis and method. We do the analysis of the structures with the help of a method which is known as finite element method, and that analysis is known as finite element analysis. So we can write either finite element analysis, or we can write finite element method. So why it was required? Okay, why FEM is required? Okay, so there will be the question. So why we require this method? I will answer you this question with full satisfaction. Okay, we know that the applications of the physical principles, like we have different physical principles like the mass balance or the energy conservation or equilibrium. We all know all these physical principles lead to some of the equations at the end. So like the physical principle, like we throw a ball in the air, this is a physical principle, like ball, we throw it in the air. Okay, we know that when we throw this ball like this, it will follow a parabolic path. If we try to plot its trajectory, or for any instance we want to try to locate its position, or locate its try to measure its velocity or anything like that, like we want to try to map its position, locate its velocity or acceleration, we all know that we have to apply some principles like equilibrium equation. Okay, equilibrium equation and conservation of linear momentum, of linear momentum and conservation of energy. We know that all those physical principles will lead to some of the equations, like the famous equation. I will simply write F is equal to ma. Okay, like we know that what is F. F is the rate of change of momentum. Dp by dt is equal to ma. You see that how this simple physical problem, like throwing the ball in the air, has led to a differential equation, finally to a differential equation of this form, linear differential equation. If you take any example, like this is our sun, and this is earth revolving around it. Okay, this is earth. We know that the governing physical principle that governs this motion of earth around the sun is gravitational force by the sun is equal to the centripetal force of earth, mv square by r. That is, if it's having a tangential velocity of r. We again see that here fg is called mv square. It will, when we solve this in the physics, we again, it also leads to a differential equation, that is dp by dt is called mv square by r. Or in any case, like the car is moving, or the things are falling towards the earth, or the heat conduction, like heat is passing from one hot body to the cooler body, or the cooling, Newton's cooling effect, or whatever there is, the flow problem like permeability problem you might have seen in geotech, or the settlement problem in itself, all and all physical phenomena finally boil down to an equation which is differential in form. That is, it involves the derivatives of the quantities. So when we arrive at derivatives of the quantity, or like you people have might be aware of this well-known problem in this dynamics, like we have a mass system like this, which is having stiffness k, simple untampered system like this, which is having stiffness k and mass m, and its position is changing like this, x, okay, and it's x of t. Some force dynamic forces are being applied on it. We know that we write its equation as mx double dot plus kx is equal to f of t. Like, you are seeing only the terms, big terms here, but if you expand this, you will see that this is m d2x by dt square plus kx is equal to f of t. Here again you say that we are having a differential equation. Differential equation comes as a result of some physical problem, okay. You see that we were having a mass m, it was being excited by some excitation force f of t externally. So we wanted to see how it's this uh, position varies as a function of time. We are not aware of what will be this function. So for that, to get this x of t, which is actually the solution of this differential equation, we need to solve this differential equation, okay. Uh, we need to solve this differential equation. But this is one of the simpler cases where we have very simple geometry like mass m, stiffness k, everything given, and we have a small geometry like ball b. And at the bigger problems like earth revolving around the sun, we have a very big picture, like we take the things at very large scale. But often physical problems do not involve like these simpler cases, like we have these simple geometries, simple boundary conditions. These things are not like that. If in structural mechanics problem, we also see that if we have a cantilever beam like this, we are applying some force F1 like this, or force F2 like this, F2 like this. Like we have simple boundary condition, fixed boundary condition at one end with this cantilever beam. So we can obtain its solution if we write it as a differential equation and then obtain its solution. It will be very easy because there is only one boundary condition, and the application of the force is also simple. One is the flexural force and another is the axial force. Since it's very simpler in nature, we can obtain its closure form solutions. But our this practical in practical scenarios, this problem never exists like this. Like we have we will be having the same cantilever beam like this, but this will not be having the shape like this. It will be like this. First section will be like this, then maybe it is tapered like this, maybe it's having some overhang like this, another part like this. So in order to deal with these problems like boundary condition, we have same, but we have a complex geometry, okay. Complex geometry, what we will do, how we will incorporate this complex geometry in our mathematical formulation, like getting the differential equation and solving, obtaining a solution for that differential equation. So when these problems come in front of the researchers or the scientists, they thought to develop a numerical method in which we will not be obtaining the solution of this differential equation in a closed form. Like for this closed form, solution is possible. Okay, possible. But if we see real life applications, real life applications involve one of the biggest problem with the real life applications is the complex geometries. Complex geometries are present there, and one more thing is complex boundary conditions. Complex boundary conditions. I write boundary conditions as BCs, which are far from the ideal conditions, from the ideal conditions that we assume in our mathematical formulations. Okay, mathematical formulations that we assume. So, in order to incorporate, order to take care of these things, numerical method, finite element analysis, or finite element method was developed. Now, you people will be having a bigger picture why this finite element method was actually developed. So, it was developed to solve differential equations which involved complex geometries and complex boundary conditions that existed in our day-to-day day-to-day life problems. So, if anybody will ask you what is finite element method, so you will reply with a conventional definition like that the finite element method is one of the numerical methods for obtaining approximate solutions of ordinary and partial differential equations. Why it's useful? Because it is powerful when dealing with boundary conditions defined over complex geometry and that are common in practical applications. That is the bookish definition of finite element analysis. So what some other numerical methods like finite difference and for boundary element method may be competitive or even superior than finite element method, but finite element method has common because of its versatility in handling arbitrary domains and availability of sophisticated commercial finite element softwares. So like there are other finite element other numerical methods as well, but this finite element method is popular because it can be used to solve any arbitrary domain, any arbitrary shape, or any arbitrary boundary conditions. And one more thing is that uh, as this is an like once we define the finite element method, we define number of steps or how we have to deal with a finite element problem. So that involves doing the same procedure again and again, again and again, again and again. So if something is to be done at a periodic, at a repeated manner, so we can easily write down a mathematic computer code for that, and then we can use that computer code. Why to do those things, all those things manually again and again? So computer codes have been developed for this finite element method a lot as compared to another numerical methods, and those computer codes are available in the form of commercially available finite element package. Like we will be having n number of finite element package. Like you have Abacus, you have ANSYS, you have LS-DYNA, and you have many more. You have Nastran, you have Patron is there. There are n number of finite element softwares. There is one more deal too is there. So there have been a lot of computer programming in this in the field of finite element method. So this has been superior to other finite numerical methods. Okay, so I will write down it here for you people that FEM is superior to other numerical analysis, other numerical methods because first, what is because first is worst its versatility in handling arbitrary domains. In handling arbitrary domains, okay. And is because another reason is availability, availability of commercial commercial finite element software over last few decades. Okay, these are the two major reasons. Let's take a small break. So we saw that why FEM is superior to other numerical methods. Now we will begin to see the other things regarding this finite element method. What are the steps that this finite element method usually involves? Okay, so we will see. We have to see the application of the finite element, the application of FEM to any given problem involves following 6 steps. So how we have to proceed to any physical problem if we require it to solve it regarding using finite element method is that first step is first one of the first basic steps is development of element equations. I will make you understand this. What is development of element equations? We have different types of elements, starting from the bar element, then we have beam element, then we have truss element, we have space truss element, or we have 3D truss element. Then we have different types of elements. We have how we develop the equations, basic equations from for one element, and then we proceed. Then second step is the discretization. Discretization of solution domain into a finite element mesh. Finite element mesh. We called it as meshing. Okay, I will make you understand what it is. First, I will write all the 6 steps, and then once we obtain the element equations for all the elements, we combine them or assemble them, which we known as assembly of element equations. After assembly of element equations, fourth step is what will be the actual boundary condition. We incorporate those boundary conditions. Okay, introduction. Sorry, is introduction of boundary conditions into the problem. Okay, and fifth step is solution of the nodal unknowns. Okay, what we assume some unknowns in element equations, then we obtain the solutions to those nodal unknowns. Solution to nodal unknowns. And finally, as a last step, that is the computation of the solution and related quantities. Okay, I will let you know. Computation of solution and related quantities. Okay, what I mean by all these steps is I will take one example how we incorporate all these steps in our finite element method. Okay, so first I will, this is the basic flow chart how we have to deal with it. Let me make it a little bit more understanding to you people. Okay, so the first step is this development of the element equations, and the second step is finite element meshing. Okay, third as a part of third step, you assemble all the equations to form one global equation, and then incorporate actual boundary conditions into the global equation. And you have assumed some unknowns at the initial while initializing the problem. Then you obtain a solution to those unknowns, and from those unknowns you obtain other quantities, whatever you have required. For example, in some problems you assume displacement as unknown. Some problems you assume slope as unknown. You will see how at different problems you assume different things. Okay, so you have this part goes to this. Okay, from this you go to this. Okay, from this you go to this. From this you go to this, and from this you go to this. This is the basic finite element method process that we follow. Basic procedure. Okay. Okay, this is the basic procedure of finite element. I will try to make you understand what this procedure is. First, I will let you know the key idea of the finite element method is first to discretize the solution domain into a number of simpler domains called elements. Okay, then an approximate solution is assumed over an element in terms of solutions at selected points called nodes. To give a clear idea, I will let you know. For example, we have a bar, we have a like it is fixed at this end. Okay, bar is fixed at this end. Okay, so for example, if it's being acted upon by some force, constant force, F like here, okay, and it is having a boundary condition like this here, okay, and it is as 1.0 and its length is L, like length of this bar is L, okay, and I want to, you know that if you do some mechanics over it, you will find the governing differential equation that will be incorporated into it is one more thing I want to mention here is that its area is A and it's constant throughout the constant and its modulus of elasticity is E, okay, stiffness is E, constant, okay, it's constant. You know that its differential equation will be looking like something like this: EA d2 by dx square of u plus f will be equal to 0. That is the governing differential equation. Okay, we call it as GD. Okay, governing differential equation. So after this equation, what we do is that, for example, this bar is of length L. What we do is as a first step is that we develop an element equation. So for element equation, we have to sorry. So uh, we have governing differential equation of this problem like this. Okay. So once we have governing differential equation, after that we try to break this problem like its solution domain is, we will see the domain of this governing differential equation is x varies 0 less than x less than L. This is less or equal to L. Okay, this is clear to you people. This is the domain. Okay, so what we do is that we will not take the whole domain. We will break this so problem into smaller elements. Like we will take three elements: element 1, element 2, and element 3. Okay, I took three elements. I took three elements of equal length, that is element 1, element 2, for you people, bigger screen, element 3. Okay, so once I took three elements, then for this nothing, I took this element only. Like I took this element, small element. Okay, okay, I took this element and first discretized it, or the divided the problem into smaller number of elements. For this element I wrote this equation. Okay, same equation for element ea d2, sorry, ea d2u by dx square plus f, force that will be applied on this element f1 is equal to 0, and it is domain is 0 less than x. This is each thing, each element is 0. This is L by 3, this is 2L by 3, and this is L then, and it will be 0 less or equal less than L by 3 for this element. I obtained this equation for this element. Then applying the finite element procedure. Okay, applying finite element procedure. This is the same governing differential equation that is applicable into this element. Applying finite element procedure, I obtained I obtained the element equation. Okay. For example, the length of this element was like, it is L by 3. Let's I take for generalization. It is L. Okay, length of this element is L. Obtained the element equation. So we will be seeing in the subsequent lectures what will be what exactly this element equation is. For time being, I will write it like this. Element equation for this one element in a bar problem is equal to EA by L. It's a matrix problem form like minus 1, minus 1, minus 1, 1. And what will be the nodal displacements? Okay, U1, U2, U1, U2, sorry, U1, U2 plus is equal to F1, F2. Like how it's like this. For example, I took the same element. This is the element like this. I assumed that it will be having one nodal displacement U1 here. It will be having another nodal displacement U2 here. And it's having a length of L. After doing some finite element mathematics like this, I obtained this equation. And one more thing, nodal forces F1 is acting like this and F2 is like acting like this here. I obtained a nodal equation like this for this element. Okay. nodal equation like this. Obtained this equation, and now this is for element 1 only, okay? Element 1 only. If I combine these equations of all these elements, like uh, equation 1, then I have equation 2 and equation 3 of 3 elements, okay? This is for element 1, this is for element 2, this is for element 3. I will get a set of equations like this. No, I call this as global system, okay? Okay, global system. That is what is written here, assemble of the element equations to form a bigger system, that is global system. In this global system, what we do is that we incorporate the boundary conditions. That is, boundary conditions are put inside this global system. Like the boundary condition here is that u at x is equal to 0 is equal to 0. It is like that. So we will be having a global system like this. We will be having matrix like this. Then we will be having u1, u2, u3 equal to something. Okay, some we will have to incorporate u1 is equal to 0 here. That is the incorporation of the boundary condition. Once we uh, import all the boundary conditions, we will get the value of the nodal quantities. Remember what we are the nodal quantities u1, u2, that are the unknowns there. The junction of any two elements is known as node. They have same nodal quantities. Okay, I will write node here. Okay, so value of nodal quantities is obtained. So for example, I got the value of nodal quantity, like I got the value of u1, it's obviously 0. Then I got the value of u2, I got something, I got u3 something something. Okay, I got the value of nodal quantities like this. Okay, that is this step, a solution of the nodal unknown. Now it's not only thing that is required in our problem, like I was not only required to find the displacements at these nodes. Actually my problem would have been like this: find stresses, find strain, find forces throughout the bar as an application of force F. So these were the quantities to be found, huh? Okay, unknowns. Okay, how with the help of this these nodal quantities I will be able to get these things? It's actually again the mechanics that I will be telling you in the coming lectures. How actually we will get from these nodal quantities, we will get first strain. Okay, after strain, you know that strain can be converted to stress with the help of constitutive relationship. Okay, okay, and you know that stress can be converted to I mean to say that force using the equation. Okay, okay, strain, you know that it is uh, change by original thing. Okay, change in length or original length. In the big picture we can write it that epsilon, from epsilon we can write stress sigma is equal to e epsilon. That's the constitutive relationship. With the help of that we can write force F is equal to a sigma, where a is the area. So you see that how by applying very basic principle starting from a very small element, how we arrived at the stress, strain, and forces in each element. And if you are able to find the force in any location in the bar, you will be able to find. So like I will be writing the equations in terms of element equations for strains as well. Like in strain, we have an equation like this, that is epsilon is equal to 2 by L minus 1 by 2, 1 by 2 matrix u1 u2. U1, U2. It's like this. And same stress can be obtained this from this, and stress can be obtained at this, and strain force can be obtained in each element like this. This is the basic finite element concept, how this finite element method works for a simple bar problem like this. Now you have the same bar problem. These bar problems will be arranged in any fashion to make a truss. You know that truss is a formation, is an assembly of the bars in different fashion. Okay, same truss elements can be obtained in 1D fashion and 2D fashion to form truss girders, and that girder can be placed in two three girders can be placed together to form a bridge deck. And how to analyze that bridge deck? You know, you have to start from a simple element in a bar element, and then come up to the forces in the bridge deck. You know that how this everything is connected, beautifully connected with the help of a finite element method. You know how of starting from the basic things where I would add the solution of such big engineering problems. So yeah, it's clear to you people that like we obtained. I will write it for you. Solution for bar. Okay, then combination of bars becomes truss. Okay, and combination of trusses becomes girder. Okay, and combination of girders becomes bridge deck. You see that how from this we arrived at, that is from starting from simple thing, it is actual engineering problem. So you got the concept that, for example, if someone tells you to analyze a beach deck, find the forces, momentus, stresses, strains in each element, you will say that, oh, what tool I can use? You can use finite element method, wherein you can start from the basic problem like bar problem, arrange those bars to form a truss, arrange those trusses to form a girder, arrange those girders to form a bridge deck. So how using very small element we can arrive elegant solutions for a major complex engineering problems. Okay, like this, like this, like this. I think our 1 hour is almost completed. If you people have any questions, you can ask. And I hope you people have got all the concept in this week session, that is week one. Thank you, everyone. And you people have any questions, you can ask right now. I thank everyone for joining this session. Hope this session was helpful to you people.